Hello, today we're going to be talking about this module that we have, the Markov chain Monte Carlo, in particular, how to use it to estimate radius of invasion if you have resistivity logs that show some invasion. Um, these are some synthetic logs that I prepared. We're going to be using UTEP wells, as you can imagine. And these synthetic logs clearly have the one that has 10 inches depth of investigation has a lower resistivity, and then the deeper one with 120 inches has clearly higher resistivity. You can probably see, you can assume there's some water oil contact down here, and then there's some transition down here. There's different levels of separation, and we want to estimate how much uh, invasion do we have. Now, to do that, we're gonna assume that we have a piston-like model. So what that means is we're gonna move to this other cross section. And what we're seeing in this plot is we have the borehole to the left, then we have an invaded zone that has a certain value. In this case, we're showing resistivity, and then we have another zone, another radial zone, which is gonna be the virgin zone. Um, all these, of course, using UTEP wells. The first thing we need to do is we need to have some boundaries so that the properties can have some variation. There's other videos explaining how to do that, and if you're here, you probably already know how to do that. Then we're going to be assuming that the first thing we're going to do is we're going to populate properties, which you do. You open that module using Earth model and then populate properties, or directly in this button that says populate properties. We're going to assume that the resistivity in the invaded zone is closer to what we have here, the low, so the shallowest log that we have. And then we're going to assume that so that's why I have M1R1, which is the equivalent to 10 AR. Then we have for the formation zone, notice this for the invaded, then we're going to say that for the formation zone, we're going to have the 120. So we're assuming that the resistivity in the invaded zone is closer to the one at 120. And then we have some radius that we have no idea where that's going to be. So we're just going to start with 0.4 meters. This is just a complete guess. And then when we do populate, that's going to set the radius of invasion the same way that that was. And then I'm going to show what it did for the other two properties that we didn't see any changes here, but that's okay. If they were in a different location, you can make these changes anywhere and then just hit populate and you go back to where you were. It's a good initial guess. In this case, I'm showing 3 logs. Now, if we were to run, that's a fair guess. That's what most people would do for any further analysis. But if you run the simulation, you give it a little time, you actually run the numerical simulation, which means that assuming these radius of invasion with these logs, we want to see how the equivalent logs look like. You see that they clearly do not match. As you can imagine, I have them with the same color or very similar, light green, dark green, or blue and blue, red and red. They don't exactly match. You can see that the red one is not that far. There are some areas where it's a little further than others. But so you could argue that the guess that you did for the virgin zone is not too bad in this area, but it's clearly wrong down here, which would lead to some uh, inaccuracies in water saturation estimations and ultimately in hydrocarbon estimations, which is probably why you're here at the end of the day. Um, so for to getting a better guess, you could just propose a different radius of invasion. Maybe we went too far, so you could just say, well, actually it was zero point 0.3. You can populate that and see how now with this more shallow radius of invasion, assuming a completely constant radius of invasion, we can see how that's going to affect the logs, and they probably even worse. So no, we don't want to do that. And you can keep guessing for a long while, but really what you want to do is you want to have something more methodic. And for that we have the MCMC module, which you open just by clicking here, MCMC. And this is what it looks like. We're going to invert for resistivity. There are some properties that you can give to the invaded zone and the formation zone. we're going to invert for all of them. So you can invert for the invaded zone property, in this case resistivity, of course, for the formation resistivity, for the invasion radius, and then you can initialize the properties from the Earth model. So from what we have, so we're going to say yes from what we have, radius of invasion and the properties. These are the tools that we're going to use. Make sure it's 2D. If you care about radius of invasion, you have to care about this dimension. Then you select the logs that you're going to match. These are the ones that I'm going to use, the same ones that you're seeing. Then we only care about making a quick match, so I'm going to do only accelerated search. 10 iterations should be more than enough, and if we get an RMSD of 1% or less, we're golden. For this tool, I know that the noise is roughly 0.3 percent plus 2 millisiemens per meter. And then I'm just going to say, okay, run. And now we're going to see that the properties are going to change at every iteration. And not only that, but the radius of invasion is going to change. And we're going to hopefully get a better estimate of that radius of invasion. This is a very simple case. The first iteration here, well, here you have some diagnosis tools. The first iteration is just with the initial guess where it is, and then you can see that it's decreasing. And that's great. You can clearly see that the match is much better. We're gonna say that's probably good enough, so we're gonna stop. This is a synthetic case. Don't expect this. Don't expect to be as good in field cases, but we've been testing it with a few sponsors. This module has been there for a while, and some users have been using it in field cases and they have gotten pretty decent results. So don't expect it to be as quick or as perfect as this one, but you're not going to be that far. And now with these much better matches, you should use this resistivity. Clearly here you have a very different resistivity, and the water saturation that you're going to calculate from this is going to be very different. Now, a couple of things to mention here. Here, you see that the separation is very small, and it's saying that the radius of invasion is higher than in other parts, but at the same time, it's telling you that the property left and right of the radius of invasion is the same. That can be interpreted as no invasion. So there's going to be three ways that the module is going to tell you there is actually no invasion. If the two properties are basically the same, just you can ignore it and it'll give you the same results. It's telling you there's no invasion. If the radius becomes too small, there's no invasion, or if it's too big, there is no invasion. If it's smaller than the depth of investigation of the shallowest log, or deeper than the deeper log, there's no invasion. Now, this has great results, and we're happy with it. Now let's go a little further and say that we don't know if this is the right answer or not, and in line with the idea that all this is piston-like, instead of populating the resistivity, let's assume that we know the porosity and we know water resistivity and so on, and we're going to populate the water saturation. So here, let me just select water saturation for the non-shale part. Water saturation for the non-shale part. And I'm going to say that the value is just 1. We're just going to say that it's totally saturated. And we're not going to do this. I'm going to populate again. So I'm going to destroy my results. Populate again. Here we are. And this guy is in a different well, it's still the results we had because we haven't modified it, but we're going to modify it now that we by the water saturation. So now that we have the water saturation, I'm going to open the populate properties, and like I was saying, assuming that I already have the right model, the right porosity, the right water saturation, MNN, whichever model you're using. In this case, it's straightforward, just Juhas with 2 and 2. And I say calculate, it's going to modify this guy slightly. The red is completely off, so we can ignore it for now. We were just the red is the virgin zone. We were only interested in this part, and we can say that this is probably closer. There's been a couple of projects with some users that we've seen this helps a lot, especially for stability. So we're not going to invert for the invaded zone. We're just going to say this is the right value. And to do that here, we're going to say we're not inverting for the invaded zone property. It's going to stay fixed. We are going to invert for the formation resistivity and for the invasion radius. Now we can initialize the properties from the Earth model. So we're just going to, we can either keep them there because that's what we have here, or I can uncheck this because we're not inverting for the blue, for the invaded zone. It's going to stay there, and the red one is going to go to the right place, let's say. Or it's going to be the same as if I just did populate. So maybe I'll just do populate. It does exactly the same thing. So it just goes to populate. The blue stays where it was. We don't have the resistivity for the invaded zone anymore. And now I can just say, okay, I'm going to take the properties from the Earth model. I can have the radius from the Earth model or not. The initial guess is just the shallowest radius plus a little more. And then I can invert using this. And if it's consistent with what I've been observing, it's going to give you very similar results. Sometimes it takes a little longer because you have less flexibility, but it's probably going to be more accurate because you have less uncertainty coming from the invaded zone. So now the first one is just, well, you have the misfit and the root mean square deviation, and it went to 1.5. That's actually really good. And like I was saying, it did get better, but it's the middle log is still not perfect. It's getting there. It'll be a little slower, but it will get to a similar result than what we had. And like I said, we can probably trust these results a little more. And let's let it run a couple more iterations, and then I'm going to stop it, and then we're just going to see the results, and that'll be it. All right, I'm going to stop it here. It's going to run one more time just to put all the results together, meaning all the local improvements are going to be combined into one last run to see the final results. And you see it's basically the same thing we had before. The match is great, and the resistivity, you can see that there's some changes here compared to the previous results. So that might be significant. And with that, thank you for watching. And if you have any questions, you probably know me, and you can send me an email or anybody else in the group. Thank you.